Warm greetings, everyone. Good morning, good afternoon, good evening, wherever you are in the world. So happy to be here. My name is Siva Velichami, and I'm from Team Amazon. And today we will be discussing the topic of network science for facility design. It's an honor and a privilege to be part of AnyLogic again. With me today, there are couple of other presenters who will be presenting along with me. So I'll start with a quick introduction. So I have about like 15 years of experience in the industry in optimization, simulation, machine learning, and I've had my background in computer science. I joined Amazon about like four and a half years back, and ever since I'm part of this group, Worldwide Design Engineering, and our role within Amazon is we design all the different Amazon facilities throughout the world. Other than my work, I am an ardent reader. I love to read books. I keep up with the latest trends in the technical books, non-technical self-help books. I read a lot. With that, I will hand over to my co-presenter, Prasad. Prasad.
Good morning. Shiva introduced, name is Prasad Rao, Director of Data and Science in Amazon. Been here for last 10 years. Before that came from an automotive domain. My skill set and experience more relates to, science simulation, material flow simulation, and product simulation. This So today what I'm going to, introduce and talk about a little bit is about, myself first and then quickly go through, what we do as Shiva mentioned, we engineer the network for Amazon in terms of our fulfillment centers. And we use a lot of, science models and principles either to validate, predict, and design, these systems. Most of our, approaches are through mathematical data analysis and models. These data models, provide some guidance on the design principles, process and flow management. Because material flow, in a fulfillment center, is very critical, and that is the heart of the whole system. And what we bring in there is with our technological tools and products, the brain to run these processes, brain to run the flow. That's what we bring in through our team. Just want to kind of briefly talk about, the design workflow, design strategy. What we typically do here is, how do we build the facility design, prioritizing business requirements, with a complex network that we have. Our business requirements are significantly changed. And how do we build a well-defined strategy as essential for achieving, cohesive outcomes in terms of some of, the critical metrics that we have related to cost, related to safety, related to speed, and so forth. Now, the other bigger tool that we build in is, validation. Validation ensures that the processes and products, meet required standards. As complex as our network, as I mentioned, is, we have multiple different processes with significant amount of interdependencies with them. And this step is very critical for minimizing errors, and ensuring overall throughput. Because one of the key measure of like the system is the throughput in the system, capacity with which like the design can deliver. As I said, this comes with a mix of process and product. This is referred to the methodologies employed in the development of product, including planning and iterative testing. What we are like designing is systems that where the capital runs into millions, and even the overall cost of this project runs almost as high as billions of dollars. How do we bring like processes that enhance productivity and design quality? That is what like we influence like in this business. And at the last of the cycle is like standards. As I mentioned, this multiple processes that we use, multiple equipments that we use. This comes with like standard, establishing the standards, and like consistently applying them drives the quality across all stages of the design and like production. Standards actually drive our decision making and evaluation. We perform it through a series of specification that are like are key part of the solution tools that we develop. The next is like how we are like what we are composed of, and how do we think like from our team. We call our team here as ideas, basically like to have innovation, data analytics, emulation, artificial intelligence, and simulation. These are like the key solution tools that we drive like and create like ideas and solve the problems for us. And we use an effective level of data layer to do that. Before handing over, I just want to kind of bring this very interesting part. What we do is like we use all of these.
Yeah. So, like Prasad mentioned, our goal is to design the facilities. And how does network science fits here in facility design, right? We have suppliers on one end, we have consumers on the other end. Between the suppliers and consumers, billions of products getting delivered. And these products were from thousands and maybe million of suppliers and millions of customers. It goes through a series of facilities before it reaches the doors of the customer. And as we track through the journey of all these commodities that flows through our network, facilities are the integral part of the supply chain. If we look at all the decisions made on every single items that are delivered through Amazon, majority of these decisions are happening under the roof. And there are of course decisions that happens when the product is in transit from one node to another node, but the amount of decisions that happens under the roof is significantly higher. What that brings is this mental model of hardware and a software. So if we look at our cell phones, there's a hardware part of the cell phone, and then the operating system that sits on top of the hardware. Facility design is more like the hardware, and we have all these decision systems that act upon this hardware to provide a better route for these products to reach through the end consumers. And when we think about the facilities, there are a lot of metrics that we track under the roof. And these are like our local objectives. We need to meet the throughput of the facility, the target, and we need to make sure when the customer places an order, the order is fulfilled in the shortest time possible. So every order comes with a promised date and time. So that those all becomes the local objectives of the facilities. And there's also global objectives. So if I were to develop like one giant model for Amazon, what are the things that we need to consider, right? Like obviously safety, whatever equipments processes and products that we put under the roof within a facility, it needs to be safe for the employees. It the fulfillment that happens should meet the speed and the quality for customers. The operations that we do uh, has to be cost efficient, and also we should be using as minimal resources as possible to be efficient from an energy perspective. So that's for Amazon purpose. And from a sustainability perspective, like we need to make sure we are sending as minimal number of trailers as possible for environment. And the last is very interesting stuff. Like sometimes we may have to compromise all the above for future adaptability and market trends. Let's say a new robotic innovation that happened, and we have to be the first player to get into the market. So sometimes it may not be that efficient. So, but still we need to prioritize that. It ties to our Amazon flywheel principle. Everything starts from customer experience, which generates traffic, and then that brings more sellers to our network, that adds more selection, and this drives lower cost structure, lower price, which again feeds back into our customer experience. And to develop such a broader view for facility design, like we need to not just look at local objectives, we have to also look at the global objectives. What are the key features that we would need in a model, right? Like we need to be able to model both micro and macro of the supply chain. What that means is both under the roof and over the road within a same model. And the metrics that we track from our simulations should track more unit level, facility level, and network level. So unit level metrics is from the supplier to the end consumer. What is the miles traveled per unit? What is the time taken to deliver? And what the facility level metrics are the throughput, efficiency, and the network level metrics is like how many trailers I'm running on a day-to-day basis. All this, like sometimes these metrics are like conflicting objectives. So efficiency versus speed. So we have to sort of do this trade-off and balance. And the environment that we are building should have capabilities to integrate various solution methods like optimization engines, ML libraries, and everything have to be integrated. Finally, it has to capture and visualize all the critical metrics. The picture speaks more than a ton of words. So these are all the key features or requirements for us to design our facilities. And to for those of you who haven't listened to our previous talk, we showcased in 2023 AnyLogic conference, how we can use simulation as a framework and integrate optimization engines, machine learning platforms, and heuristics to solve same problem. So what we are essentially doing is creating the environment, plugging and playing these different models to make better decisions both under the roof and over the road. All this is good, but let's say if we wanted to scale it to a bigger network, this is huge, right? Like with the amount of the this products that we are delivering, scalability becomes an issue. So we started using multiple different tools and leveraging their superpowers. AnyLogic is one of the major tools. We also use another multi-threaded simulation environment called Simudyne. So how we use Simudyne and AnyLogic together in building this uh, big framework of simulations is the Simudyne model computes what happens under the roof and over the road uh, in a same model, because it is multi-threaded and it has the computational capability to churn those data. AnyLogic is used for some inputs, like to get the GIS distance between every single node. And AnyLogic is more like a testing ground for us in order to integrate these bigger models. So let's say if I want to change my current algorithm to a different algorithm, I test it like an A/B testing within AnyLogic. And if that algorithm works good, then I integrate it within the bigger model. And finally, this model doesn't have good visualization because it was heavily based on compute. So we skimmed off all the visualization elements in it. And finally, we use this data produced from this Simidyne model we use AnyLogic to extract the metadata or the trailer level and create visualization, something similar to this. So what we see here is like all different facilities within Amazon and the trailers that goes from each of these facilities. This is about a week worth of trailers. This is just the inbound network. I'm gonna skip this video in the interest of time. So there are multiple case studies we did. In 2023, we evaluated uh, the big network change on the inbound side for inbound regionalization. And then 2024, we evaluated mode of transportation using this approach. And in 2025, which is the current topic for discussion, we are evaluating outbound loading and containerization strategy. So with this, I will hand over to the next presenter, Mahek here, to talk a little bit on this particular initiative.
Okay. Hi everyone. I'm Mahek. I am a part of the design team in Worldwide Design Engineering. Thanks, Prasad and Siva. So I think on the outbound loading types, the figure on the left illustrates the different modes of outbound loading that we use currently at Amazon's inbound facilities. The first one is called fluid load, which we use a lot of. Basically means that we are creating a wall of containers of cases inside the trailer without using a container as such to bind the cases into the trailer. So in this case, the trailer itself is the container, and we are trying to utilize and max out the cubic space as much as possible. While this is like very efficient from a transportation perspective, it is an inefficient process in terms of associate safety, as well as the time it takes to load the trailer. The second loading type from that is the hybrid load. In this case, also we are building a fluid wall, but instead of just using cases, we are now using the yellow totes, as we call them, and then the cases. We put the yellow totes at the bottom to provide a firm foundation, and then the cases on the top. This provides still a very good utilization of the trailer, but inefficient in terms of, again, building the wall and the amount of time it takes. The third one is more standard across the industry, which is the palletized loads. In this case, instead of fluid loading, we are palletizing all our cases. And then based on the palletization, we are basically double stacking them if the height of the pallets does not exceed a certain threshold. And then we are able to fit as many pallets as possible. The next one is the fluid loading again, but this is for totes only. In this case, again, the trailer is the container, but we are only loading the totes in a fluid fashion, provides better utilization. And the last one, contrary to what the picture shows, is actually a palletized load, but that only contains totes instead of cases. Um, so these are the different loading types that we have. As I mentioned, I think the pros of fluid loading are predominantly the increased trailer utilization that it gives, which is an important business metric. But the cons are safety challenges and then variability in process paths, as well as just the amount of time it takes. So what we did is try to evaluate through this network science simulation what increase in trailers would need to the network if we convert all those fluid loaded cases to palletized cases, and then also how to still achieve a higher amount of trailer utilization while doing that. So the picture at the bottom shows like an outbound dock configuration. In this case, we are palletizing everything. So we have a buffer of packages that are arriving to us from the conveyors. And then we have multiple bins. These bins can be thought of as pallets or containers in which we are palletizing. And we want to create a bin packing algorithm in a way that provides us the best container utilization, in effect, giving us the best trailer utilization. Um, Currently, 60 to 70% of the trailers that we have utilize fluid loading, and the remaining is palletized. The trailers that utilize fluid loading are also very heavily utilized. what we wanted to study was if we convert 100% of these trailers, the 60 to 70% of fluid laid trailers to palletized trailers, how will it impact the trailer utilization and eventually the number of additional trailers that we generate? So for that, Siva did the network science simulation as well as the bin packing, which he can walk us through.
Thanks, Mahek. So this is like the classical 3D bin packing problem. So we simulated 2 weeks in history, and our goal is to quantify the impact of converting all the fluid load to palletize. And these are some of the assumptions on the tote dimensions. So converting tote fluid to tote palletize, it's a simple arithmetic. Like every pallet contains X number of totes, but when it comes to case pallets, these cases or boxes of different dimensions. There are like 6 different orientation we can place these box. And our goal is to maximize the utilization of the bin in that configuration picture Mahek was talking about. I'm not going to go into the details of the models in the interest of time, but we have placement constraints, which is making sure that all the boxes are placed, and also it makes sure the boxes are not going out of the bin. There are non-overlap constraints. So this is an extreme point method where we track all the extreme points of the box, and we put constraints that we are not like really violating the physics. And similarly, the support constraints, like let's say one box is bigger and the other box is smaller, and we want to put like a bigger box on top of this. We make sure the surface area at the bottom is adhering to the physics. And finally, like the bin closing condition, when do I close the bin and move it to the staging area? With all this, we are trying to maximize the utilization. The order is n square, but still, since we are only going to evaluate a handful of bins, the complexity is not that big of a challenge for us. So the key takeaways are like enhancing the efficiency with this new setup. Like what is our future going to look like? And what we found was 100% versus the 85%. Like when I do 100% conversion of fluid to pallet, I add hundreds of trailers. But with eliminating the top few arcs, we can reduce that additional trailers to like from hundreds to a handful of trailers, which is a significant reduction in the amount of trailers. Now another advantage to this is now pallet utilization becomes a function of number of open positions for the pallets, the options that I have when I pick a box to load. What are my different options? And we can easily have a robot do all these palletizing activities. So with that, what's next from a simulation perspective, right? Like everybody is actually talking about AI, and one of the books that I read from David Krakauer, he talks about complementary cognitive artifacts versus competitive cognitive artifacts. There are tools that are like a calculator, which offloads some of our mental work, cognitive work, and there are also tools that helps us get smarter, like Rubik's cube or a sextant or those type of tools which makes us smarter. Like now with AI and simulation together, um, how are we using this powerful tool more as a complementary artifact wherever it is applicable, and also wherever it is applicable, using it as competitive artifacts, and help us get smarter from where we are. So I'd like to end it with that note. And thank you so much. And there are a lot of people who contributed to this. So that big thank you to the internal team Amazon and all the people here.